we're going to start talking about some annoying stuff because SQL is actually a pretty annoying language, but we're going to start talking about how we implement SQL today. We talked about the pipeline, the query evaluation pipeline last time, and remember that we start with some text, and I'm sad because this is CS122, and yeah, we're learning databases, but you guys don't get to learn parsers, and it's kind of weird that Caltech teaches you parsers in the graphics class. What is it, 176 or something like? I can't remember, but you have to write an object file parser for that one. Do what? Not anymore. Great. So it's like, let's eliminate all knowledge about how parsing works. But anyway, hopefully for 123, if you do 123, you'll get to have some experience with modifying the parser for NanoDB. But anyway, so we won't talk about the first or the second step. Hopefully you know how to write the first step. Then abstract syntax tree taken care of for you, and then we have this whole process of translating that into something that can actually be fed into the evaluation engine. And so you can see that there's several problems that we have to solve. We have to figure out how to implement the relational algebra operations. And most of them are straightforward, so we're not going to talk about that yet. We're going to actually push that off until later. We have to talk about how to translate the SQL abstract syntax tree into some kind of corresponding relational algebra plan. And then finally, we have to figure out how to actually evaluate and generate results. Now, in sort of true Caltech style, we're going to talk about these in the opposite order that I have them listed here. So we're going to talk about the last one first, and then the second one, and then we'll get back to the first one. Mainly because there's a lot of details that will fall out of the discussion when we sort of approach this problem in reverse. So we'll start talking about how we evaluate these things, just in general. We have various ways of actually implementing these plan nodes, as they are called. Okay, and like I say, you can have different representations for the SQL translation step and then the execution step, or what comes out of the optimizer. Some databases actually represent those as different things. And so you might have something that's purely abstract initially when it comes out of the SQL translator. A lot of databases do this. Okay? And then what happens is that during optimization, the optimizer goes in and annotates and says, well, I want this select to be an index scan using this index as opposed to a file scan. And here's the predicate that I want you to apply. So that's one thing that some databases do in generating these plans. And in those cases, notice that the annotated plan node, that is the one that can be used in evaluation, is called an evaluation primitive. Because the evaluation primitive can be used to evaluate the plan. And we talked a little bit about this in 121. I don't know if you remember this because it was an awful while ago. But things like file scans, or implementing a select plan node, a project plan node, a grouping and aggregation plan node, or a natural join or a hash join plan node. And when those things are annotated with all the details that are necessary for evaluation, it's called an evaluation primitive. Okay, so that's that. Now, other databases, and I think I have a little note here that says it. Yeah, this is what NanoDB does. It sort of comes out of the gate with a plan that could be handed straight over to the executor. The reason why we're going to start there is because our initial plan optimizer is going to not exist because we don't know how to optimize things yet. What we're going to start with is naive translation, and then we're going to try to make it more clever as we get along in the term. So like it says here, all generated plans contain implementation details, but the initial version just may be very dumb. So we always do file scans, and maybe we put predicates on those file scans, maybe we don't. Maybe we always keep the predicates higher up in the plan, and we just use simple naive translations. We always use nested loop join. We never try to optimize it initially when we're generating it. So that's another approach. And then what the optimizer does is it works with that plan comprised of execution primitives and tweaks it to make it into a faster plan. Okay, so you have these two general approaches that are taken. We're going to take the second one just because it's a little bit simpler to think about. And yeah, the implementations are called evaluation primitives. I mentioned this earlier. The thing also to keep in mind is that these tend to be multiple relational algebra operations packaged up into one plan node. And I want to mention that as well. But we have something like this. Select star from T where A equals 15. Okay? And pretty much throughout CS122, we're talking about multi-set operations. So T is a multi-set, or a bag of tuples, if you will. The select will produce a multi-set, projects produce a multi-set, unless you actually go and say select distinct, or you do something like, do a select with a grouping and you group by all of your attributes. That also implicitly does duplicate elimination and so forth. Or you do set operations, which implicitly eliminates duplicates. Then we fall back to set operations. But in general, we're talking about multi-set operations. So if T is a heap file, which it will be at this point, we can do something like this. This is our plan. And these are evaluation primitives, so it doesn't correspond directly to relational algebra, but it's pretty close. But we have a file scan node T, that's that little can thing. And by the way, if you're not familiar with this, we frequently indicate data files or databases as little cans. So T is a little table, and we're going to go ahead and suck all the tuples out of it, and they're going to pass through this select plan node, which is annotated with A equals 15. Okay? So we could do that. Okay? That would make sense. And these would be two different components in our database system, or two different evaluation primitives. So that allows us to do certain things, and it disallows us from doing certain things. And this is what we have to think about, because if we have here, for example, T being a table that has an index on attribute A, or T happens to be a sequential file or a hashed data file that includes attribute A. Let's say it's a sequential file where A is one of the first attribute in the search key, or it's a hashed file where A is the search key or the hash key. Are we able to take advantage of that with this present arrangement of things? Because think about conceptually how we might implement this. We have a file scan that sort of blurts out the contents of T, and then we have the select node above it filtering the contents of T, or whatever comes out of the plan node below it. If we have an index, we can't really take advantage of the index with this arrangement of things. And you'll notice that a lot. When you see plan nodes, there will be implications of where we apply things. We'll talk about another example of that momentarily. But we could also just create a file scan node and have it apply a predicate for us. So we could do something like this. And this would allow us to take advantage of our indexes or any other alternate file organization that we might have going here. Okay? Now, we still haven't actually made our model that much more complicated yet, because what we're talking about is a file scan with a select above it versus a file scan that acts as a select. So that's really not that much more complicated. But we can start looking at various other examples. Here's one. We saw this one. We used a non-equijoin for finding the maximum values in a table in week 1 or week 2 of last term. So this would be select star from T is T1, T is T2. Notice now we have renaming where T1.A is less than T2.A. So we have something like that. So the question is, should we actually have a separate rename plan node? Or should we make file scans and other plan nodes able to also rename at the same time, so that the plan node becomes sort of an aggregate of a number of relational algebra operations? Okay? So NanoDB happens to have a rename plan node, but that doesn't mean that's the only way that you have to do it, because it turns out, let me see if I have this note here, plan nodes have to generate what their schema is. And that was the whole reason why we like the relational algebra, because every one of these relational algebra operations clearly defines what the result schema is. And it also defines what tuples appear in the result. And so in this case, we could just have the little can that produces T say, and by the way, the result schema actually has table name T2 as opposed to table name T. And same thing with the left can. We could say the left can schema is going to apply the rename so that we don't need a separate rename plan node. Okay? NanoDB happens to have a separate rename node just so you can plop it in and it's really obvious what's going on. But then that's the whole point of NanoDB, is that it's going to be obvious. So you have these kinds of questions that you have to answer in your implementation. Now another thing, theta join. You noticed that last time, previous slide, we had Cartesian product. Not an ideal way of doing this, right? because we're going to generate a lot of extraneous tuples that we don't actually care about. So it'd be really nice if we could somehow move that conjunct down further in the tree so that we can actually apply it earlier and generate fewer rows. So frequently what we do is we implement this theta join plan node that can do a whole bunch of different things for us. You can configure it to do inner joins. You can configure it to do left outer joins if the plan or the implementation actually supports it. I'm trying to think. All of the different implementations of join that we talk about support left outer join really easily. Okay. Right outer join. Well, how do we do that? Well, we'll talk about that in a second or in a couple lectures. Full outer join can only be done with certain implementations. Okay, we'll talk about that again in a little bit. But you can't do, for example, full outer join with nested loops easily. So that version of theta join wouldn't necessarily have that option. Okay. Of course, you can always make them do Cartesian product as well, and so forth. So let's say we have something like this. Select star from T1, T2, where T1 and T1's A and T2's A are the same, and T2's B is greater than 5. We could have different plans that we generate. And again, this is just a graphical way of representing this. We could write this out as a text expression as well, but it's nice to draw pictures because it's easier to understand sort of the flow of information in the plan. So we can do something like this, where we have file scans of T1 and T2. The theta join just does a Cartesian product, and we apply our join condition and also our other predicate at the select at the top. We could also do this, where we push down the equijoin onto the theta join, and hopefully the theta join can take advantage of it. Or we could do something like this, where we actually completely eliminate the need for the select at the top because our file scan plan nodes are able to also apply predicates. Okay, so is everybody convinced that these all generate the same results? Hopefully that they are all actually equivalent. We haven't talked about equivalence rules yet, but we will. What else do I want to say about this? You can also imagine that these three plans could generate results in different orders. And frequently you'll see that kind of thing where using different implementations of theta join will generate results in different orders. That's why we like SQL to not impose ordering constraints on us unless the user actually says ordered by whatever. If we have an order by whatever, then we have to impose an ordering. We can choose where we want to apply ordering. But if we don't have any order by, we'd like to generate results in any order we prefer. And that allows us to have more options as far as optimization is concerned. Okay, let's see. So these were our three options. And yeah, so we can implement a theta join node that we can use in all these different circumstances and in other ones as well. Okay? Let me see what else I say here. Yeah, so this is basically just reiterating what I said before. There actually turned out to be a couple of other join operations that are very helpful as well. You'll see them mentioned in the second blue bullet point here. Semi-join and anti-join, or anti-semi-join, if you will. We'll talk about the need for those. Basically, it allows us to encode exists and in subqueries more efficiently. So semi-join and anti-join actually become very helpful. And I don't know if any of you have had this experience yet, but if you work with Oracle, which is a very good database system, and you have exist or not exist subclauses, or you have in or not in subclauses in a query, and you ask it to explain its plan, you may see semi-join or anti-semi-join plan nodes show up in the execution because it's a very common way of optimizing those kinds of queries. But anyway, if we can do all of this with one theta join plan node and just tweak its configuration, then that gives us a lot of power. And the result, like I have here, is that we can do a large range of queries without having large, complicated plans, which was a characteristic of the relational algebra. And we also don't have to implement a huge, like 50 different kinds of plan nodes. We can have like 15 and accomplish just about everything we want to do. Okay, any question about evaluation primitives at this point? We are not talking about how to implement them yet. Most of them are not that exciting, but we will talk about that in the future. Mainly because the reason why we're not talking about it yet is because we also want to understand the relative costs of these things. I/O costs, CPU costs, because we need to use that in plan optimization. And so we'll go ahead and talk about those things together and not get into that discussion quite yet. Okay, now this was the previous example. All I really did here was add a project. So I used to say select star from T1, T2, but now I say select C from T1, T2. And we would probably translate it into something like this. So how do we evaluate this plan? We have several different options again in how we do this, and you will see these different approaches in various databases, although there are common ones that are used by most database systems. But here's one possible approach. We have this plan, and we try to traverse it in some order, like I say here, a post-order tree traversal would certainly work fine. And what we do is we take each plan node, and we evaluate it entirely. We take the plan node, we take its input, we generate its result, and we save it somewhere. So we could certainly do that as an approach. So evaluate T1 becomes itself. That one's pretty obvious. The left can. Okay, so that one's an easy one. That's a no-op. The right one, though, what we do is we take T2 and we feed it through this plan node and we generate another temporary file that is T2 but with the select predicate applied. So now we have rows where B is greater than 5. So we generate that into some temporary storage. And then we take the two inputs to the theta join and we generate the results from applying the theta join into another temporary storage. Okay, so notice we take the theta join T1A is T2.A and we apply that to T1 and temp1 containing the results from filtering T2 and we generate another table. And then we take that result and we project it down to C, and again, this is a multi-set project, so we may see duplicate rows in that. That's fine. And we use that to generate a result, and then we take the result to send to the user or whatever. Okay. Now, there's a couple of consequences of this approach, right? Let's presume that data doesn't fit in main memory. It's good to carry that presumption through this class. So if this doesn't fit in main memory, we're generating a lot of extra IOs with this evaluation approach. Does everybody see that? Because we have to generate this thing and then generate that thing, and we have these intermediate results we have to save somewhere, so we're generating a lot of extra I.O. when we do that. Okay? So that's definitely not an ideal thing for this situation. But this approach does have a name, and it is used. I don't know if you've heard of Teradata, but Teradata is a company that's very, very successful. And one of the Caltech trustees is actually used to work with Teradata or helped found Teradata. I can't remember. But they use materialized evaluation for very specific reasons in their database product. So materialized evaluation, basically, each results are materialized or realized or reified into some temporary storage, possibly on disk if necessary. And then we go ahead and consume that result in the next plan node. So what are the issues? Like I was saying before, I.O. increases immensely when you take this approach. It's just kind of obvious that you have that. Okay? So materialized evaluation is one option where I generate each plan node's results. Another approach is pipelined evaluation. And what I do is I actually keep intermediate state of all of the different plan nodes in flight at the same time. So now I'm actually generating results tuple by tuple, or you could do it disk block by disk block if you want to. There's easy optimizations to actually achieve that, and it gives you some big benefits. We'll talk about that when we get to nested loop join. But basically, all of the plan nodes have intermediate state. They're all in process of evaluating their results at the same time. So that's pipelined evaluation. Are there any questions about materialized evaluation at this point? Okay. We won't use that. That's not what NanoDB does. But it is a very simple way of creating a database system. And particularly when you have parallel evaluation of plans, it's actually a really good idea to have parallel systems or parallel processors generating an entire result or an entire subplan's results all by itself. So that is materialized evaluation. And it's really helpful because it allows you to parallelize things. You don't have plan nodes waiting on other plan nodes or subplans waiting on other subplans. But most databases don't actually use materialized evaluation for the bulk of their evaluation. Now again, with pipeline evaluation, we're generating results tuple by tuple now. There's a couple of different ways that we could do this. We could have the situation where somebody is sitting on top of the plan and says, I want another tuple. Give me another tuple, project node. And so what happens is the project plan node says, I need another tuple. It turns around and asks its child, give me the next tuple. And the theta join turns around and says to T1 and T2, give me tuples until it's finally able to produce a result. So that's demand-driven pipeline evaluation. So yeah, top-level output, this is basically just what I was describing. So request a row from the project. The project turns around and asks the theta join for a row. And obviously the theta join can't produce a row until it finds two rows that match. And so it keeps scanning through T1 and T2, doing its magic theta join stuff until it's able to generate a joined row, and then that goes up through. Okay? Does everybody see how that works? This generates far less I/O in general than materialized evaluation, because we basically only need to keep one disk block of T1 in memory, one disk block of T2 in memory. The theta join doesn't have a lot of overhead. You could say it requires one block if you want to store tuples in buffered memory, or if you just generate literal tuple values, and that makes it easier. And same thing with the project. Very small memory overhead, very little I/O overhead for pipeline evaluation. So this is a very, very nice way of doing things. Okay. Yeah, so that's actually a really good point. The bottom right can, like the file scan, when the theta join asks T2 for a node or for a tuple, it's got to scan through the file until it finds one that satisfies the condition. So basically, you only do as much work as you need to when it's actually needed. Now, you can also have producer-driven pipelines, where you actually drive things from the bottom up. And this tends to be very, very common in parallel databases because you don't have an easy way of coordinating between the various subnodes executing parts of the plan. So I mentioned materialized evaluation appears in parallel databases. Producer-driven pipelines also appear a lot in parallel databases. And you have some kind of queue because now you need slack. You can see that T1 can generate rows very fast because all it needs to do is scan through them. T2 may be slower because it's got a filter. And then the theta join is going to be much slower. So you need queues to help buffer the rows that come, that are sort of percolating up through the plan. So yeah, this is what I was describing. So the planner hands subplans or individual plan nodes, but subplans tend to be the best choice for reasons that we'll talk about momentarily. And different processors or different computational nodes execute portions of the plan. And then they just generate tuples, and they send them out. And so, again, you're still doing pipeline evaluation, so it's got less I/O impact, but you're just pushing them out over a network communication or into shared memory or something like that. They're queued up somewhere so that the consumers can go ahead and consume them as they are able to. So we're talking about simple at this point. So this is 122. And so we'll talk about sequential databases that are not doing parallel execution of plans. And so we tend to do demand-driven pipeline evaluation. That's what MySQL does. That's what Postgres does. That's what, I expect that's what SQL Server and Oracle and DB2 all do as well. They all have parallel execution as well. They may do something different in those situations. And like I said, Teradata and Netezza are two examples of companies with database products that deviate from this, because they both do parallel databases. Okay, any questions about pipeline evaluation? Now you'll notice that there's certain situations where you have operations that can't be pipelined. Can anybody think of an obvious one where you have an operation that can't be pipelined? Where you actually have to consume all of your inputs. Yeah. I'm sorry? Correlations make your life miserable. Let me think. Is there correlated evaluation? Correlated evaluation is sort of orthogonal to pipeline evaluation, I think. Yeah, I mean, what you'd like to do is decorrelate that, and then you don't care. But in the case of correlated evaluation, what correlated evaluation does is it sort of requires you to restart evaluating subplans, which you can imagine with materialized evaluation would generate even more IOs. And with producer driven pipelines where you're shooting out tuples, you might have to throw away a lot of intermediate computations that you didn't use. So correlated evaluation definitely muddies the waters, but it is still pretty orthogonal to this whole issue. Yeah. Yeah, grouping can definitely have that effect. Did you have that or another one? Well, you can so we'll talk about grouping in a second, but yeah. Yes, exactly. Well, you have the max. But the thing is that if you have all, well, I don't want to get ahead of myself, but grouping, we'll definitely talk about grouping. Are there any others that you guys can think of? Yeah. In and exists, we'll talk about those in a couple lectures. It depends. Like exists really just needs to find one row. Yeah, not exists could be bad. Not in could be bad. Definitely you could run into situations like that, yeah. Ordering, sorting. Sorry, was your answer stolen? Solomon? Okay. Oh, do you have a different answer? Or? Outer joins, you can definitely run into that with outer joins as well. That's a very good answer, actually. Nested, well, we'll talk, I don't want to get ahead of myself. All of these are very good answers. We'll take two simple examples. Grouping and sorting, because grouping can be implemented with sorting as well. But you imagine a situation where you have an order by in your query. Well, in that situation, the sort plan node blocks everything above it until it's consumed all of its inputs. It's just not possible to evaluate it any other way. So like I have here, let's say select star from T where A is less than 25, ordered by B. Well, the sort plan node must materialize its input. Everybody see that? Because I have to see every row to know where, which row is first and which row is second and so forth. I have to do it. There's no way around that. Okay. The same thing is true for sort-based grouping. Actually, no, I got it backwards. It's interesting. I'll talk about that in a second, hopefully. Yeah, blocking operations. Some databases do take blocking into account. Postgres is an interesting one because it actually keeps a couple of estimates. One estimate is how long will it take to generate all the results, and the other one is how long will it take to produce the first result. Because if you have something like a top n query, I want to find the top row or the top 10 rows, then it makes sense to minimize that time to generate my results. I don't care. I mean, I do care more about blocking operations than I do. I'd like to apply blocking operations when the input is as small as possible to make that as fast as possible. Okay, so that's one thing to consider. So yeah, the reason why I didn't, let me see if I talk about this on the next slide. Yeah, so you have operations that can be implemented in two different ways. So grouping and aggregation. Let's try to unpack this beast. We have select username, sum scores, total score from game scores, group by username. So we could have a corresponding relational algebra expression like this. I think that plan would execute pretty easily. So if the incoming tuples are already sorted on the username, this is why it's a little bit backwards, and this is why it's a little bit confusing, and that's why I was like, oh, how do I explain this? But if the incoming tuples are already sorted, is the grouping and aggregation going to be a blocking operation? I see a few shaking heads. The answer is no. Because remember, the tuples are ordered by the grouping attribute, username in this case. So I can scan each group's values and then generate the result for that group when I see the next group value show up. Which is really weird because the sorting version of group and aggregate is not blocking. The hashing one is. Because I don't know, I may see some tuple that corresponds to some group way down in the results. I can't generate the result for that group until I actually consume all the inputs. So it's kind of an unusual thing. If I have to sort internally. So this is the reason why it's a little bit confusing, because if I have a sort-based grouping and aggregation, that plan node is not blocking, but there may be some earlier plan node that's blocking. In this case, there probably would be, because I'd have to sort. But if it's a hash-based grouping and aggregation, it's always blocking. Now, the reason why sort-based grouping and aggregation not being blocking is helpful is because I may be able to do my grouping and aggregation by scanning an index. And if I have to scan a sequential index, it's not blocking at all. I can start generating those results right away. Because I already have the data sorted. It got sorted earlier. It's stored on the disk in a sorted order. Okay? Does that make sense, everybody? A lot of subtlety here. Thankfully, for none of the assignments do you actually have to care about estimating time to first row. We just have to generate an overall CPU cost, an overall I/O cost, and use that for plan optimization. But we don't care about some of these more subtle things because NanoDB is simple. Okay, so enough about blocking operations. Yeah, so are there any questions about what we've talked about so far? Because now we're going to start talking about how we actually translate this stuff. SQL is a horrible language. And so we have nested subqueries. Some of you have already mentioned that, in, not in, exists, not exists. There are actually set comparison operations as well. Some of you may be familiar with this, but you can actually have a comparison operation and then say sum, any, all, and then a subquery. So you can say, is this less than some value in the subquery's result? I don't like to talk about that stuff because it's really gross, and it turns out to be really hard to optimize as well. So I just sort of pretend it doesn't exist. But there you go. You know, you can see what real databases do with that kind of stuff. But we have correlated evaluation, which technically doesn't have to affect SQL query translation unless we want to be fast. If we don't care about being fast, correlated evaluation is easy. Subqueries are easy, and we'll talk about some little shortcuts for doing that probably on Friday. But grouping and aggregation are terrible. Grouping and aggregation make you want to shoot yourself. So we'll talk about some simple examples, which you will recognize from CS121, where the basic syntax maps to relational algebra easily. But there's a lot of nuance that we really don't talk about in CS121, just because SQL is a nuanced language. It requires some careful thinking. Select star from T1, comma, T2, comma, whatever. What relational algebra would this translate into? There's no where clause. There's no grouping and aggregation. It's just what it is. Cartesian product of T1 with T2 with whatever follows T1 and T2. So that one's simple. Now we have a predicate. What do we translate this into? It's not complicated, guys. Come on. Yeah, so we wrap a select around what we just had, right? With P as the predicate. So that's simple. Now we're starting to get a little bit more complicated. Select E1 is A1, E2 is A2. So we have aliases that we're applying to our expressions from some set of tables that are cross-producted together, which is probably not useful. What would this be? Yeah. Yeah, we do a project after our Cartesian product. So we're okay so far. E1 is A1. And, we do all the clever stuff where we can have whatever functions we want in E1 so that we actually can have useful functions, coalesces, and concatenations, and sine or cosine, or whatever we want to do. Various simple functions. And then this one. Where does P go in the picture? This is where we start to get complicated. Does anybody know what the SQL standard says about where P goes? Yeah. Yes, the standard says that the select goes between the project and the Cartesian product. This has some implications we're going to talk about. One thing I wanted to say about this just went out of my head. But anyway, let me show you this at least. What did I want to say about this? I'm sorry? Duplicates? No, I don't need to say anything about duplicates because we don't care about those for a while. I can't remember what I was going to say. Oh yeah, I remember now. I have a copy of the SQL standard, which I will make available to you. You should be happy because the SQL standard costs money. And, well, I found it on the internet, so now you can have it too. You will be unhappy when you read it, though. It makes me want to gouge my eyes out every single time I try to read it. But it answers a lot of these questions. And the other thing that I probably will apologize for as well is that the SQL standard uses functional dependency theory to describe a lot of relationships between values generated by joins. How do you determine what are keys coming out of queries? what grouping and aggregation is allowed and so forth. Uses functional dependencies everywhere, so it's kind of cool to see that. But anyway, I'll make a copy of that available for you to look at if you'd like to. Okay, so we have this. Select E1 is A1, E2 is A2, and we have this. The reason why this is confusing is because most databases allow us to do things that violate this translation. Okay, let me show you an example. Select A plus C as V from T where V is less than 25. Many databases allow you to do this. I believe Postgres does. MySQL definitely, MySQL doesn't have any rules at all. It's like, what the? But this is an interesting thing. This is actually not an ANSI standard SQL query. If we were to follow the above mapping, then we would end up with something like this. Yeah, it doesn't make any sense, right? Because now we have select V is less than 25, but we haven't computed what V is yet. So what do? Do we put the project before, and then you can easily write other queries that break it when you put the project before the select. Thankfully, the standard is just very clear about it. The predicate is really only allowed to refer to columns from the from clause. Now, what columns are generated by the from clause? Well, we'll talk about that next lecture because it's another complicated topic. But in this case, you can see if we restrict ourselves to ANSI standard SQL, we actually do ourselves a favor because we require that the predicate has to refer to where A plus C is less than 25. We just are required to. Okay, but we can do the other stuff. I just want to mention this because it depends on how sophisticated or clever we want to do our SQL translation. So, for example, we could go through the select clause and say, oh, they have this name V, and V is defined as A plus C. So anywhere that I see V, in places where V is really not allowed to be, but hey, we're trying to be friends here, then we'll go ahead and plug that in. We'll go ahead and translate that in. And of course, you have to remember to do this on clauses, because you can have whatever you want in on clauses. They're not constrained to only be join conditions, although it would be nice if you did that. You can put where conditions in there too. Okay, having clauses can certainly refer to V as well. If you had group by and then having later, you could do that. So that basically allows us to follow the standard mapping. Basically, the definition of what that select query is supposed to mean according to the SQL standard. Okay, so that's just one little note here. Any questions about that? This is only the beginning of sorrows. It gets much worse. Grouping and aggregation. Here is a simple sort of template. So select G1 through whatever, and then E1 through whatever. So G1 and so forth are grouping attributes, or grouping expressions, I should say. And E1 are expressions that involve aggregates. And then you have some where predicate, and then you have a having predicate as well. Okay? Now note what I say here. G1 and so forth are expressions that we are grouping on. They are not required to be only column references. E1 and so forth are not required to be just a call to min, a call to sum. You could constrain it that way and you probably wouldn't eliminate the ability to generate various queries, but your life would get far more complicated because then this would have to be nested in something else so that you could then do those computations. But like I say, it approximately maps, which is funny because in CS121 we're like, this is what it maps to, but it's more complicated than this. So we have our Cartesian product inside for the from clause, we have our where select predicate, we have our grouping and aggregation applied, and then we have our having predicate applied after that. Roughly that's what we do. The problem is the G's and the E's that we have to figure out. Okay, they're not required to be simple column references, and E1 and so forth are not required to be aggregate functions. And the having predicate is also allowed to contain aggregate expressions as well. So for example, it's not uncommon to see people who write queries that are like, select some aggregate expression from some tables, some joined tables together, group by some grouping attribute having some other aggregate, let's say count greater than 3 or something like that. so that we have different aggregates in our select clause than our having clause, and we don't have the grouping attributes appear anywhere except in the group by clause. Totally allowed. And so we have to figure out how to translate that. Here's an example. One that would make me groan. Select A minus B is G, so that's our grouping value, because you can see group by A minus B. 3 times, and then we have this other thing, min of C plus max of D times E from our table, having, and then we have another aggregate expression in the having clause. Okay? So you see that this is a little bit tricky. We need to figure out how to disentangle this because it's just not possible to map this straightforwardly into our mapping that we had on the last slide. Okay? And like I was saying, the reason is because select also includes aggregate expressions and projection. It mixes those two things together. Having includes selection and aggregates. And group by generally is well behaved. Group by is one of the things that you can anchor onto in this situation. Okay? So we need to translate this query in multiple steps to actually get it into a form that we can turn into a relational algebra expression. Are there any questions so far? Anybody ready to quit? Okay, good. It's not horrible yet. It'll be horrible when you have to implement this, but it's actually pretty straightforward. I'll tell you exactly how to do it. So we have this initial query, and the first thing we need to do is go through and identify and extract all of our aggregate computations, because remember, this is what we need our grouping and aggregate node to do. And we will replace those things with placeholders, our favorite thing in the world. It's funny how many CS122 concepts are really obvious here. Naming things so that we can refer to them later, compute them separately, and then plug them in. Okay, so replace with auto-generated column references. When I do it, I like to use some kind of name that users can't type so that the name spacing is really easy. So I do something like preface it with a pound sign or an underscore or a dollar sign or something like that. So we can rewrite this query as select A minus B as G 3 times this magical quantity A1, magical quantity A2 from T, and then you can see in the having clause we have another magical quantity, A3. And then we have their definitions also recorded separately, because we need to use those in generating our grouping and aggregate operation. Okay? Do I want to say anything? Oh yeah, so double quotes. This is the reason why I hate MySQL for accepting double quoted things. Double quoted terms in SQL are supposed to be column references or column names. Single quoted things are supposed to be just data, string data. But double quoted is supposed to be column names. It allows you to have case-sensitive columns. It allows you to have column names that are keywords. It allows you to even do some crazy stuff like this, like use non-standard characters for column names. So this is why I get really upset in 121 when people use double quotes instead of single quotes, because this is important. Yeah. Backticks, that's a good question. Do you remember what their meaning is in SQL? Yeah, you know what? I do not remember if they have a meaning for specific vendors or if they have a meaning in the standard. Does anybody else know? Does anybody know about backticks? All right. I would have to do some research to find out the answer to that, because that's a good question, but I don't know the answer to it. Okay. So, yeah, it may be that MySQL has a special meaning for that, but it's not meaningful in the standard. I'll have to look at the standard. Okay, but anyway, everybody see what we've done so far. Now, this SQL is no longer valid. We're not allowed to use this anymore because we don't have any definition of what these things are. You can imagine probably a larger nested query that actually does these things, but I didn't want to waste the slide space on that. But you could easily do that yourself. But we do know what aggregates we have to compute now. Now, we have that, and we can translate that relatively straightforwardly. Okay, notice whatever's in our from clause, and we're simple here, so just T, so we just plug that in to the grouping and aggregation. We don't have any where predicate, so why generate a select with true under it? So we go ahead and just have T, and that feeds into grouping and aggregation. Our group by A minus B is applied there, and we have our grouping expression. Min C as A1, max D times E as A2, sum of F as A3. And then we go ahead and feed that into our select. And now we've actually done both the group by and the having. Well, actually, we've done the from, the group by, and the having. We still have to do the select, right? Questions? Okay. Then we just wrap it with a project. So again, for the sake of slide space, I didn't do that, but you can see we have project. We just follow the select query, or the select clause. A minus B is G, because we wanted to give it a name. 3 times A1 plus A2 as, and then we give it some name. Because you'll notice here we didn't name it. The provider of the query didn't provide a name for that weird 3 times min C plus max DE. So we have to figure out what to call it. And that is an implementation-specific choice. Okay? So some databases, most databases, in fact, will generate a name based on the expression contents. So it would be very common to see somebody rename that as 3 times min C plus max D times E because that explains what it is. Most databases do that, so that's a very good choice. I don't think NanoDB does, just because I was lazy, but it would easily support that. Because you can turn an expression into a string just as easily as you can turn a string into an expression. Okay. Or, yeah, you could call it something like unnamed one, which I think is what NanoDB does. It just generates an unnamed column name to hold the place for that. Okay, any questions? All right, I am playing fast and loose here, so you guys should call me about on this. We have this translation. What issue do we have? Well, besides it's gross, which is unavoidable, unfortunately. Don't worry, it gets worse. Wait till we talk about joins. Start seeing coalesces pop up here and there. Does the grouping and aggregate operator actually produce a column A or a column B? It doesn't, right? It produces this aggregate, or not aggregate. It produces a computed result that is A minus B. And then we project, in the generalized project, this expression A minus B as G. This is still sloppy. This is playing fast and loose with the translation. This is actually not allowed. Which is gross. Okay. So, a little bit of an issue, but it's relatively straightforward to solve. Basically, we just need to take our group by clause and take each one of those things and give it a name as well. And then we can plug placeholders in the select so that our final generalized project only refers to stuff that's produced by the grouping and the aggregation. So we could do something like this. And then if we follow this translation, so now notice that we've identified, our dog has very long hair. So we have this G1 now is A minus B. We haven't substituted that in, but we can go ahead and do that. So now we have select G1 as G, and then in our group by we have group by A minus B, and an implicit, we give it the name G1. Then we can go ahead and do the full translation, and we have no problem. Okay? Do I expect you to do this level? Yeah, probably not. I'd like you to be able to support the aggregate refactoring because that's pretty important. It allows you to do a lot of powerful stuff. But the grouping stuff, I'll probably make an extra credit thing. It's not too hard, but it still works. Okay, now the other thing that you'll notice about this is that if I have this translation of my group by, I can also start doing stupid things, like select 3 times the quantity A minus B, group by A minus B, which is allowed because 3 times the quantity A minus B is functionally determined by A minus B. And I'm allowed to do that. The SQL standard allows me to do that. So, yay, I guess. But anyway, this is how you get to the full grouping and aggregation support. Are there any questions? All right, so that's one thing. We have just a few more minutes, so let me see. Yeah, so this is an ANSI SQL query. So this is just referring to the whole group by A minus B and how we can't use group by G here because that is not going to be allowed by the standard. But still, you have databases that can do the non-standard stuff. MySQL can, Postgres can. SQL Server is very strict about this. So you apply the same techniques as before. You just record aliases, and then you do the translation as you're going through and doing things. It's very helpful. A lot of people really like it, so that they don't have to repeat themselves. Yeah, I speak English good. But you know, it's a helpful thing to do, but I probably won't require that for any of NanoDB because it's like, why? That's just starting to add busy work. So, but just be aware that you can support these things relatively easily. Okay, let's see. Join expressions. We'll go ahead and wrap up with joins really quickly, or at least introduce the topic. But we talked about this form, and that's all our examples that we use. Select whatever from T1, T2, and so forth. And there's no way of specifying outer joins. That was one of the beauties of the original SQL standard, or the SQL language as proposed by IBM. You couldn't do a lot of the complicated things that we can do now. But you just have this list, which kind of suggests that your abstract syntax tree just needs to maintain a list of tables. But that will never do, because we have all of these other join operations we can do. T1 join T2 with an on clause, a using clause, natural join clause, and so forth. And of course, we can have modifiers on the join. Inner, left, right, full outer, cross join, and I think that's basically it. Okay? So you can see that joins become a lot more complicated to support than just having a list of tables that are joined together. Yeah, and you can even have stuff like this. Select star from T1, comma, and then T2 left join T3. You can certainly do that kind of thing. Hopefully you never have. Hopefully you'll never need to, but you can. And so basically the way to view join operations is that they are binary operators. And so my from clause specifies a binary tree that has an ordering on the way that the tables are joined together, as well as these other modifiers. It's an outer join, it's an inner join, it's a cross join. Okay? Like it says here, operate on two relations. They're left associative. And so when you have this comma, now the comma becomes a join operation, or a join operand. And you can view that as a binary operation as well. You just make that a lower precedence so that these A join B stuff gets grouped together like multiplication does. And then the commas do cross products between the various other join sub-expressions. Okay? Does that make sense, everybody? Yeah.
So would you have to compute the T2 left join T3, that part of it before you can calculate the rest?
That is a very good question. Do we have to do the T2 left join T3 first? In general, that is the order that the user specified. So the results that you generate must match whatever the order that the user specified. We are allowed to rearrange many, many things in SQL. But the fact that we have an outer join here constrains us. And we'll talk about some of those constraints in probably a couple weeks, when we start talking about equivalence rules and how that affects outer join reorder. Because inner joins we can rearrange however we want. We don't have to do it literally in the order they specify. We just have to generate results that would match the order that they specified. But outer joins really complicate things. You might remember there was a problem on either assignment 1 or assignment 2 that got into some of that. Can you evaluate outer joins in any order? Okay? Any other questions? All right, let me see what else I say. Yeah, so last slide, we'll just do this really quickly. Yeah, so you parse your from clause into a binary tree, and you can use parentheses if you need to overwrite it. You is the writer of queries. And it's straightforward to translate. It's not straightforward to optimize. And but there are some nuances in this as well. Okay? So what we're going to do next time is we'll pick up this topic, and we'll talk about outer joins as far as translation, and we'll talk about natural joins. Because again, natural joins make you want to cry a little bit. So we'll talk about all of that next time. All right, see you guys.